Hello and welcome to our latest webinar of BYK Instruments. My name is John Kowalski. I'm part of the marketing team here at BYK Instruments. I'd like to welcome you. Today's presentation is a deep dive into media milling. This is the second part in our Dispersion series. I'll put a link to the first part from our YouTube channel if you'd like to listen to that. But anyway, this presentation will last approximately 45 minutes. We may have some time for a couple questions at the end. If you do have some questions, please log them in the chat box located in the bottom right-hand corner of your screen, and we'll get to them time permitting. If not, we'll follow up with you directly afterwards. Also, we are recording this webinar, and immediately following, you'll receive an automated email with a link to this. Feel free to watch it later, share it with colleagues, whatever you like. So with that, let me introduce our presenter. He's Mr. Andy Stummer. He is our business line manager for Dispersion. Take it away, Andy. It's all yours.
Thank you, John. Hello and welcome, everybody. Like John said, this is the second part of the dispersion seminar. So the last time we talked about the pre-dispersion, the first step in that process. And today we're going to cover the media milling component. But before we go into the actual milling part, we're going to have a little bit of an overview and just give you an introduction about the company VMA and where you're from and the relationship with BYK. Then we're going to briefly just talk about the dispersion process, the pre-dispersion process, before we dive into the media milling part. And then we're going to talk a little bit about the different lab and production equipment capabilities that we offer for our media mills, a little bit about the quality control and upscales. And then at the end, we're going to close it off with discussing and showing you some of the laboratory capabilities we have in Wallingford, Connecticut, at BYK USA, our sister company, and also at VMA in Germany. And you can see right here on the picture, we cover, our product line covers everything from laboratory scale to pilot all the way up to manufacturing. And so VMA Getzmann, they're the owners of the Dispermat brand. The company was founded about 50 years ago by Herman and Elke Getzmann. Herman is still, believe it or not, involved in the business. He comes in the office at least once a week just to make sure that the designers still follow his design philosophy and that the company is run well. BYK has had the distribution rights for North America exclusively since 1988. The company is still owned by the same family. The two kids are running it, Christian and Martin. Over in Germany, they have a total of about 100 employees. That includes also some of the, agents that are covering some of the other parts in the world. And they are known to be high-end manufacturers of dissolvers, speed mills, basket mills, and again, everything from the lab space all the way up through pilot and then all the way up to production. So here is a good picture that kind of gives you an idea about the company. They are located about 40 miles east of Cologne, so kind of right in the heart of Germany. They're all over the world. One of the nice things about their product line is that they do a lot of custom stuff. So probably about 40% of everything that VMA manufactures is custom. There's so many different requirements these days. You start from pigment development to, renewable energies with batteries. There is a lot of milling that needs to be done in, different types of environments. They don't want any air with vacuum systems. So there's a lot of customization that goes into making these products. So at least 40% is custom. And then we have some really nice laboratory space here in the US at our sister company, BYK USA, that we'll show you at the end, where you can actually come in and do some trials with your products. So just to get in right away, so why are we actually dispersing and milling? So bottom line is we really want to improve our products. So when we pre-disperse, so we want to improve our wetting, these invisible binding forces, they call Van der Waals forces, they keep our particles together. Um, they're like these electromagnetic forces. That's what we're trying to break up. And then ideally, we want to reduce them back down to the primary particle size. That will result in better color strength, better gloss. Our overall appearance is improved. We're going to save money because we're going to improve on our pigment or particle efficiency. We're going to have reduced raw material costs because we need less of that in our slurries. It's going to lead us to have a much better product and more consistency, formulation improvements, and then obviously, if we do a good job milling, we're going to have the right particle size as well as very consistent particle size distribution. It's very important. And if we achieve that in the lab space, the goal is to also be able to upscale it and then have the same results in manufacturing. So if we don't do a good job, obviously, then we're going to have problems. And some of the problems that are going to come up are obviously our color isn't going to be right. We're going to have poor color stability. Gloss is going to suffer, maybe even haze. We're going to have flocculation of our pigments. That's usually an additive issue. So we have a number of different additives through our sister company, Big USA. They have a lot of different options for the different formulations. We can help you there as well. And then obviously sagging, leveling, settling, some of the other issues that come up if we don't properly disperse and mill our materials, as well as reduce gloss levels and then separation. Just these are just the main ones. There are other ones that are not listed, but it's very important that we do a really good job with our dispersing and milling process. So here is an example of why it's important. We have on the left, you can see a drawdown on a Hegman. So we are looking at something that's just pre-dispersed with the cowl's blade. And on the right, we have something that's properly milled. Same material, just one step further on the right, and on the left, we stop right after using the cowl's blade about 30 minutes into the process. And on the right, we milled this material for 2 hours, and look, it looks much, much better on our Hagman grind gauge than it does on the left side. So we really need to watch out that we have good stability in our process, that brightness is there. That will also give us the best color. And the rule of the thumb is the smaller my pigment particles, the better the quality of my product. And obviously, if I use less of, if I'm able to increase my surface area, I need less pigment or particles. Therefore, I'm saving money by using less of that material that obviously purchasing likes to hear, because we are more cost effective when we actually make this material, especially manufacturing. Viscosity is always important. Usually we want to be as low as possible. That will give us better milling performance. But keep in mind, if our viscosity is too low, it's very difficult to put in a lot of energy. And therefore, we need to find a sweet spot. And usually that's between 3 to 5,000 centipoise is where it's optimal to do the milling, because we are really able to put in a lot of energy. The product flows really well. We'll get that donut effect in the pre-dispersion process. That's that visual cue that you'll see when you look in the container, and then obviously doing the milling process, we just make the product even better. So it's really important to remember that we are not trying to destroy particles. We are only reducing the particle size by breaking up these binding forces, these Van der Waals forces that are holding these particles together. Obviously, there are some applications where impact is important, like for example, some silica products or some battery products where you really are looking for that impact. So you got to dial in the equipment to meet those specifications. But when we're talking about pigment particles, we're really just trying to break up these binding forces and not destroy our pigment particles. So We want to reduce the agglomerates, which are the larger clusters, down to the aggregates. We do this with the Coul's blades. And then from the aggregate level to the primary particle level, this is where we actually would do the media milling, which we'll cover today in detail. And it's really just the shear forces that are produced inside of our container or mill where we are actually able to then reduce these particle sizes. And then at the end, we need the right additives to keep our particles in a suspended state and so they don't flocculate back together. Here's a good slide just showing you some different types of pigments that are out there and what that primary particle size looks like. So just an example. So I really like this slide because it kind of shows what we're talking about. So when you look on the bottom here, that larger circle, these bigger, call them building blocks or blocks of particles, these are what we call the agglomerates. So when we pre-disperse our material and we use a Coul's blade, we are breaking up these binding forces at the agglomerate level to turn these particle clusters into aggregates. What we're doing there is we're also wetting our solid particles, and then we're going to end up with the aggregates properly wetted in our slurry. When we want to go from the aggregate level down to the primary particle level, the shear forces of our Coul's blade or dissolver are no longer sufficient enough to break up these aggregates. So that's why media milling is the second step in the entire dispersion process and really critical to get us down to that primary particle size. And then can't mention it enough that stabilization of our particles at the end of the milling process is really critical, and the right choice of additive is important. So this slide here kind of shows you the steps. First, we use the dissolver with the blade. We're wetting, and then when we are ready to do the milling, we then move over to the right medium milling type. We'll cover those, and then obviously the stabilization at the end. So here is a good slide just showing you the working ranges of a dissolver versus a bead mill. So a dissolver is really important to get us through the first step, the de-agglomeration stage. And then when we reach about 10 microns, it depends on the formulation and the particle size, should be anywhere between 10 to 30 microns. Anything smaller is really difficult to achieve with just the Coul's blade. That's when we really need to start the milling process. And you can see with the right medium mill, we're able to go down sub 10 microns and then all the way down into the low nano range. There is a lot of special applications in the renewable energy world, for example, where they develop coatings. These are separator coatings that go in these solid state batteries where they really need very, very small particle size. So the medium milling obviously is really critical to get them there. So when we look at the two steps of the dispersing process, we covered the pre-dispersion process the last time, a few weeks ago, and today we're going to talk about that fine dispersion process. But I want to mention that it's really important to remember the 18 to 25 meters per second of tip speed. That is critical to properly pre-disperse our slurry. And when we get down to the 10 to 30 micron range, this is when we start the medium milling or the fine dispersion process, as some people call it. And our tip speed is a little bit slower, and we're going to look at between 10 to 16 meters per second when we're milling. And when we're milling, we have some choices depending on the formulation, depending on the viscosity, whether we want to use a vertical bead mill, whether we want to go with a basket mill, or we want to use a horizontal bead mill. So there's a number of options that are available to us depending on the type of material that we're trying to mill. And we're going to talk about that a little bit later. Very important, just to review in the pre-dispersion process, is the vessel size to dissolver disc diameter. should be about 1/3. But depending on the viscosity and obviously the blade type, you have a range. And you can see on that chart on the right, where we actually, if you take, for example, a 2000 milliliter container, it's about 2 quarts. I have the ability to go from an 80 millimeter blade all the way to a 40. So the sweet spot probably be around the 60 millimeter blade diameter, but I can use something up to 80 or down to 40, depending on the viscosity of my material. The goal is when I choose that blade that I'm able to actually see a donut in my container when I'm optimizing the pre-dispersion process. Again, 10 to 25, 18 to 25 meters per second of tip speed is what we're looking for in the pre-dispersion process. Here is a good formula on how to calculate the tip speed. That formula also is true when we are calculating the rotor speed when we are milling. So it's actually the velocity is equal to pi times the diameter of my blade times the RPM of my rotor or dissolver shaft. If I calculate meters per second, I divide everything by 60. This is a really important formula on our higher end equipment. This value is actually shown on the display, so you don't have to figure that out yourself. On the lower end models that are very simple, that number is not shown. You will have to calculate that value. But it's really important. Some customers still tend to only look at RPMs and not look at tip speed. Tip speed is much more important because if I have a constant RPM and I change the diameter of my blade, I have totally different results because my tip speed will be very different. So it's really important to look at that. Again, 18 to 25 when we're pre-dispersing, 10 to 16 when we're milling. So here is the infamous donut. That's a great picture. That is exactly what I want to see when I properly pre-disperse my material. Again, sweet spot, 3,000 to 5,000 centipoise. Doesn't mean I won't get a donut at higher uh, viscosities, but that's just something that is ideal. And this is what you want to see when you optimize that right tip speed window. So optimizing the pre-dispersion results depends on the number of factors. So obviously the duration of our dispersion process. So we are looking anywhere between 15 to 30 minutes. That should be enough to then allow us to move over to the milling process. We want to see the donut effect. It's not always present. Again, depends on the viscosity, but ideally, this is what we want to see when we are dialing in the parameters correctly. Tape speed again, 18 to 25 meters per second. I always mention it because it's really, really important. Geometric consideration again, 1/3 diameter is the rule of thumb of our disc to container vessel diameter, but depending on the viscosity, this can change. Also, there is different type of impeller discs on the market. There's a lot of custom designs out there. So depending on what works best for you, you have to play around. We have a wide range of different impeller discs available in our portfolio, and you can find them on our website. The amount of mill base is critical, so we always recommend about 50% fill rate in our container, up to 70%, and as low as 40. Don't go over 70 because if you introduce the shear forces, you're probably going to spill the material. And if we use a basket mill, you don't want to go with 70 because as soon as you lower the basket mill or immersion mill into the container, you will automatically probably spill as soon as you turn it on. So try to stick around 50% fill rate in the container. Pigment filler concentration, very important. So that's a formulation discussion. When we are, pre-dispersing, it's not as critical, but we want to be able to cool our mill base. If we add more time, means more time is more heat. More heat is not good, especially when I'm running solvent-based products. So I try to keep the temperature as low as possible. So we have double-walled vessels with cooling jackets that allow you to do that. Now, there are formulations where actually the opposite is true. In some cosmetics applications where you would want a higher temperature to get better flow into your product. So there is also the ability to heat up these vessels that help you get better flow to your material. But when we talk about pigment dispersing, we prefer to have usually at lower temperatures. Um, Obviously, the additives again will give us better wetting, better dispersing, and no flocculation. And that will also help us do a better job when we are milling if we have the right additives in our formulation up front. There's also defoamers that are helping us keep the foam down. We do offer some vacuum solutions to remove the air so you won't have any foaming, but foaming can be critical, so that's an important additive to consider as well. Then, when we reach that particle size, again between 10 to 30 microns, depending on the formulation, that's when we actually start the milling process. And in the milling process, we'll be able to put in a lot more energy with our rotor and beads. We further deagglomerate, we break down the particles to the primary particle size, which will give us a much better product, as you've seen on that slide early on that Hagman drawdown, where you could see the difference between just the pre-dispersed product and the milled material. The dissolver with the cowls blade is critical. It's the first step, but it'll only be used to deagglomerate these larger agglomerate clusters. We can only put in a limited amount of energy because we don't have any beads and no milling disc, no primary particle breakup, but it is critical that it is done. And if we stop there, then we're going to have just a poor looking product. So milling is always critical. So what actually happens inside of a bead mill? So we have a bead mill, which is either at a horizontal setup or in a basket mill. Some people call it immersion mills. So we have kind of a closed container where we introduce our mill base. And inside of this vessel or container, we have or basket or milling chamber, we have beads. So now, as our rotor is turning at a higher speed, these speeds start drifting around and colliding towards each other. Now, through that drifting motion at these high velocities, you can see on this picture these particles binding forces are broken up. And that's how we are reducing the particle size inside of our mill. We are not trying to actually break by impact the pigments. We wouldn't want to destroy the pigments. All we want to do is have enough shear to break up these binding forces. And this is where it happens is as these beads collide at high speeds, that shear stress will cause these particle binding forces, the van der Waals forces, to be broken up. It's very similar if you think about when you were a kid and you sat in the bathtub and you had a rubber duck to play with, and then you tried to squeeze the rubber duck with your hand as you squishing your hands together. It wasn't easy to catch that rubber duck, right? The rubber duck would always find a way just to get away from you. That's kind of the same thing scenario what would happen inside of the bead mill, but at much higher speeds and much smaller rubber ducks or particles. So, but that shear motion is actually critical to help us break up these particle sizes. Um, so, again, it's very important to have the right additives in our formula, but if we mill long enough and we have the right media size, we should be able to get down to the primary particle size eventually. But we have to watch for a few different things. So, number one, we need to also use the right type of media. So, we have customers sometimes they go out there, they look at, glass beads, for example. They're inexpensive or relatively inexpensive, uh, but they have some problems. And some of the main issues are they're not very heavy. So, you're not going to put in a lot of kinetic energy. They break easy. Their specific weight is low, so not going to help you build up a lot of kinetic energy, even if you just increase the speed and you can't increase the rotor speed indefinitely. There's a limit. So it's very important when you want to have good milling results that you also pick good media. We recommend that you use zirconium oxide beads, cerium or yttrium stabilized, depending on your application or how hard they need to be. But that's really important. Look at also the hardness. If you have a glass bead, your wick hardness is about 400, and zirconium oxide 1150, 12, almost 3 times harder than a glass bead. So that means also the bead will wear much better, will last a lot longer, and you will not end up with shards in your mill base, which is a huge problem for a lot of customers when they have to, screen out these glass shards that are inside of the slurry. So always try to go with the better media. And then obviously there's different media sizes. Media size always depends on the particle size where I'm at. And then I want to select the correct media to basically work with the particle size. So if you want to go down to, let's say, 100 nanometers, I wouldn't use a 1 millimeter bead. I would go down in bead size all the way until I have enough uh, kinetic energy and also time to break up these particles. There are zirconium oxide beads now that are actually smaller than zero point 0.4. You can now go down to 0.1 millimeters for ultra fine applications. But that really depends on what kind of formula you have. So kind of think of it this way: how important the weight of our beads are, or this, the type of bead. For example, glass versus zirconium oxide ceramic beads. If I look at this nail and I have a board on a small hammer, with a small hammer, I'm gonna need a lot of impacts to drive that nail into the board, and it may never even get in there. If I take a large hammer, maybe one blow and it'll be in the board. That's kind of the same philosophy that you need to think about when we're talking bead selection. Okay, so more beads or heavier beads will give us better milling performance, because we're able to have higher kinetic energy. And here's a formula. Maybe you want to write it down. Just the kinetic energy of beads during the milling process is the weight of our beads times the rotor speed squared divided by 2. That would give us the kinetic energy of our process. Um, I like this slide because it gives us a good view what happens when we're milling. So these larger circles are actually our beads, and you see these aggregates. These are the smaller cluster, that smaller circle on the left that's squeezed in between the two larger circles. Uh, Once we mill and these two beads drift together at high velocities, that shearing stress will break up these forces and we'll end up with these smaller particles. That's kind of what happens. It happens in these corners as these beads collide. So as my particles are getting smaller and smaller, I should also then lower my bead size. And you will find out very easily when you're milling. Let's say we start out with the 1 to 1.2 millimeter bead. And you, let's say, get down to, you started at 10 microns and now you're at 2 microns. And you got there, let's say, after 2 hours of milling. Could take longer. And let's say you want to go now below 1 or 2 microns. You want to get into the nano range. Let's say we want to go to 700 nanometers. You have two options. Either you stay with the 1 millimeter bead, depending on the slurry, it may take you a long, long time to get there. Or I just reduce the media size to, let's say, a 0.4 to 0.6. And that will then allow me to better mill and faster mill my material and get down to my 600 nanometers. And then I do the same thing again if I want to go lower, until, bead size makes no difference anymore in my particle size. And when you're milling, you should see that because we are increasing surface area, so extended milling time should show us also that our energy is going up when we're running at constant speed, because we are producing smaller particles, so we have more surface area. Therefore, we should see that our energy consumption is going up in the milling process. That means we are actually continually milling down the particles, and that's really important. So these are the critical, factors when we are milling. So again, 10 to 30 microns particle size. When we're done with the dissolver, that's the starting point. Bead size and weight. Okay, always get the heavier beads. Bead type. So there's a lot of different beads on the market. Use the one that's best for your formula with the right hardness. But again, zirconium oxide beads are probably, the best type of beads on the market. Bead loading really is important, but that depends on the type of milling equipment you're using. You're using a vertical bead mill where I can add a lot more beads. Where in a basket mill I have less beads, uh, and then you have also up to 80% bead loading in a horizontal medium mill. So it really depends. The shape of beads, you always want to screen your beads over time. Beads wear, if you use really inexpensive beads, even ceramic beads, you can end up in various shapes. We have seen them actually show up oval right out of the box, and ideally they should be perfectly spherical if you get a good quality bead. Milling again, tape speed 10 to 16 meters per second. Product temperature is very critical that we monitor it, and we want to have really good cooling because as we are introducing this energy, when we are milling, a lot more energy than when we're just pre-dispersing, we want to be able to cool our product. So it's really important to have a good chiller, have a double wall container. If we use a basket or immersion mill, and also a cooling capability with our basket mill. And then on the horizontal mill, they all have good cooling anyways. But you might also want to have a supply vessel if you do a recirculation method where you're also able to cool the mill base as it comes back and circulates through the supply vessel. Energy input is important, is how much energy I'm actually putting into my slurry. So some of the equipment give you the ability not to only run at a certain speed, but also run with a certain amount of energy. That's really important, especially when you want to upscale. You may want to look at that, say, hey, I want to run this, let's say, with 2,000 watts or 3,000 watts of energy instead of 5,000 RPMs. So then if you keep your energy constant, then what happens is the machine or the device will adjust the speed or the rotor speed depending on our change in viscosity. The number of passes. Am I going to pass through a recirculation method in a horizontal mill or in a basket mill? Obviously, how often does my material circles through my basket? That's really important. The milling time. How long do I mill for? Depending obviously on the milling system, on the slurry type, on the volume. All these play a critical role in my milling time. But the bottom line is I'm done when I reach the desired particle size. And that really depends on your formula. Um, the viscosity of the mill base is very important. Don't be too thin because it's very difficult to put in the energy to help us with the breakup. And if we're too thick, then it's very difficult to feed the material through the mills, whether it's a horizontal mill or a basket mill or vertical bead mill. So I want to have flowable material. Um, the diameter of our rotor or milling disc is important. The material, for example, some color sensitive applications, if you want to produce a white product where you can't have any, this cross contamination of if the rotor was metal, stainless steel, it would over time bleed into your slurry. And for renewable energy products or white materials, you can't have that. So there is zirconium oxide or silicon carbide rotors or milling discs or lined milling chambers that will avoid the cross-contamination of the steel. So that's really important. And then again, the type of mill design, whether I'm talking vertical, horizontal, that's really, really important. So just a quick slide. So the Dispermat, that modularity, what I mentioned earlier, is really important for us. So one base machine will give you the ability to do many different things by just buying the right attachment. So on a standard Dispermat, you can acquire a rotor stator, you could get a vacuum system, you could get an APS, which is a vertical bead mill. We'll talk about that in a moment. Wall scraping system, or the basket mill, tourist mill, TML on the bottom right is also an attachment that would go right onto the base Dispermat. The Dispermat will get shipped the way you see it, just a standard dissolver shaft. Then obviously you have to pick a blade that fits your container diameter. The smaller Dispermats come with blades. The larger models, they do not come with blades. You have to pick a blade out of a portfolio, and then that'd be a separate item. Okay. So here's an example of a laboratory disperser with that modular capability. You can see that quick change system on top, where you can actually remove that clamping ring and then have the ability to just pop in a basket mill or vertical bead mill on the same disperser. They can go up to 20,000 RPM in the lab space. Some of them can be explosion proof depending on the model. We also have the ability to add software. So what you're looking at right here is that high-end model with that C control panel, which is really nice. It gives you the ability to store batches by name or product ID number, and you are really able to monitor all the different variables that are important in my milling or dispersing process, such as my speed, my energy input, my torque value, time and temperature, are all displayed right there. I can also program what's called cutoff values. If I have temperature sensitive materials, and I have, let's say, at 60 C or 80 C temperature limit, I can program it so where the machine would warn us at some point before it reaches that temperature threshold. And once it reaches it, maybe shut down or run at with a different energy input or a different speed. So that's really important, and you have the ability to set that up with that C technology. So that modularity allows us to have a base dissolver. The Dispermat can function as a homogenizer, as a mixer, propeller with the butterfly tool, or we can use it as an emulsifier with the rotor state attachment, or as a disperser to do the pre-dispersing and milling. Everything can be done on one machine. So get back to the milling process. So here, showing you the TML basket mill in more detail. So when you look at that picture on the bottom, that's actually a really nice cross-section of our TML. You can see the double-walled milling chamber. So we have cooling lines that go through it to properly cool our basket. And we have a screen on the bottom right below the milling disc. And then that will allow us to keep the beads inside of the milling chamber so they don't fall out. Right above the milling disc, I have a pumping and steering wheel. That is patented. That is actually important because it creates a vortex that will allow the mill to suck your mill base into the basket. That basket obviously would get filled with beads, and then you're running that 10 to 16 meters per second of tip speed, and then you will be able to do a really good job milling down your particles. So as you're milling, you can see below the screen right there on the bottom, there is a cowl's blade. Now that cowl's blade has the function of drawing the mill base out of the basket and pushing it back around to the top of my container, where then that pumping and steering wheel would take over and draw it back in. So you should have a really good flow and motion of or circulation of your mill base in and out of the container and have a very effective cooling in the process. Now, as you probably know, if you're using immersion mills or basket mills, there's some competitors out there that are actually, you have a design where the screen is on the side and not on the bottom. Now, we purposely opted against this design because this is where most of your beads will flow and impact the side wall of your basket or immersion mill. Now, that would mean that if you had a basket, you had a screen on the side, that would lead to higher wear of your screen, and needs more parts need to be replaced. Um, it's important that the screen is on the bottom so you have less wear, but more importantly, this is where all your energy would build up. So if you have a screen right there, you're not going to cool your mill properly. So it's very important that that part of the mill is properly cooled with these cooling lines. Therefore, we cannot have a screen right on the side, or we could, but we don't think it's a great idea. Therefore, our screen is on the bottom, and it's really, really efficient for these reasons of cooling and wear efficiency. Um, Basket mills, great tools, very easy to clean, very nice to operate. If you have the right viscosity range, obviously you can't use something like this if you are running thick pastes that are hardly flowing, because they would not end up in your basket. They would just kind of sit on top of your vessel, and it would be very difficult to draw them in and out of our basket. So as long as you have a formula where your material flows properly, even at very high viscosities, as long as, like honey, if you turn over the pot and the honey flows out of your pot, you can use a basket mill. If it doesn't flow anymore, if your slurry is non-flowable, this is not an option. Um, with the standard setup, we can go down low micron range, higher nanometer range. With the nano kit that's available, we can go down to about 500 nanometers with the basket mill. Anything smaller than that, we are no longer able to use a basket mill, unfortunately. This is when a horizontal mill is a requirement to really properly pre, uh, break up this aggregate down to the primary particle size. But very, very good for small, jobs in your lab, and excellent for production when you want to go upscale. Very scalable. We have the upscale ratio almost 1-to-1 uh, with our TML. Here you kind of see on that picture on the left the flow of the material in and out of the basket, and how important that cowl split is on the bottom of our mill. And you can actually see on that graph the beads are inside of that milling chamber. Here is just a quick slide of a production scale. That screw right there allows us to feed the media into our basket. Stainless steel, high polished. Our cooling lines are actually inside of these bars that are holding the basket, and there is a third bar behind that would actually have a PT100 probe to actually measure the temperature inside of our basket, where it's very important to measure it inside because that's where we're putting in all the energy. Again, very small quantities, all the way up to 2,000 liters in production. Perfect or really, really good upscale ratio from our labs models, pilot to manufacturing. Easy to clean. Probably a quick clean takes you about 10-15 minutes in the lab, maybe half an hour if you really take everything apart and do a thorough cleanup, but a lot quicker and easier than I would have with the horizontal mill. Patented pumping steering wheel to get that vortex, easy, simple design, not a lot of wear parts on there, no seals, no O-rings like you would find in a horizontal mill. So very, very operator friendly. And again, that cooling efficiency is really excellent with our basket mill. Here is an example of two production size basket mills with an integrated dissolver. These are called tourist mill TMs. The awesomeness here is that you basically never have to move your container around. So you have one container, you start pre-dispersing right there. When you are done, your particles are down 10 to 30 micron range. You push a button on the control panel, and the basket that you can see comes down, and now you're milling. The dissolver discs are behind the gentleman in the gray. They haven't been installed yet, but basically this is a 2-in-1 system that is really, really awesome if I have limited space and I want to do everything on one machine. So that capability doesn't exist only in the lab space. We have that also in production. Then we have the APS vertical bead mill. This is really a cool device for the lab space, not scalable, where I have two containers. I have the container on top and on the bottom. And I have a better picture here. So if you can look at the picture on the right, basically I have my slurry in here. I would also, it's already showing you that with the milling rotor, before I mill, I can pre-disperse in here, but just changing the tip with a cow's blade. And then when I'm milling, I just pop on my milling discs or my milling disc, depending on the design. Add my beads. I can add 100% bead loading. So if I have, 100 milliliters of slurry, I can add 100 milliliters of beads. So I have a lot of beads in there for excellent milling performance. Should also give you quick milling performance. And when you're done with the milling, just open that drain plug on the bottom. There's actually a screen that separates the media from that container below at the mill base. And then you just hook up an air line. There's a socket in the cover, and you pressurize the container, and then you're actually purging out your slurry into that container below. That is your milled material. And then when you're finished, you just pop the drain plug back in place. At that point, you should only have the media left in that container. Add maybe a cleaning agent, either solvent or water base, and then run it again and drain it and rinse and repeat until you have a clean vessel. So this is a very easy way of milling. I can go up to about 7 liters depending on my vessel size and Dispersion model, but this is not really scalable up to production because how would you ever be able to have had 2,000 liter production run, or container size? You would add a ton of beads, literally 1 ton. That's almost impossible to manage. So this is great for the lab space. Quick check, quick small sample production. Really, really good, but again, not scalable. Just a bigger slide, same thing we just talked about. So here you can see that cover with that air socket right there. We would hook up the air hose and then you pressurize the container. There's also a clamping ring that goes around it to secure the cover to the container so it doesn't pop off when you are applying the pressure. And then we have obviously a line of horizontal mills. We call them Dispersion SL and RS for production. Also with the C technology panel here on the right. And then we have an explosion proof panel on our production. On this picture, we have non-explosion proof models also. We can go up in, different chamber sizes. Really good, nice design, very compact. We actually have the option of doing pass-through or recirculation method, depending on the formula. We have an integrated pumping and steering system inside of our supply vessel that allows us to actually push the slurry into our milling chamber and get it through and around. The models go up to 6,000 RPM. Separate motor controllers so we can independently control the rotor as well as the pumping speed. Again, different options there for the rotor or the liner, ceramic, hard metal, or some people use some plastics even, polyvinyl or, polyurethane options as well. Wide choice of media sizes available for the standard model. We have a nano kit that you can purchase for the standard machine, or we also have a standard nano machine as well that allows you to really go down to the super small particle size that you may need for certain applications. Just quickly, here's the C control panel. We have these cutoff values, program capabilities we talked about earlier for temperature sensitive products or products where I only want to put in a certain amount of energy if running, with a constant speed. And if I'm running with constant energy, I can have a speed limiter also as part of my cutout value programming. So it depends. You can modify it depending on how you want to run the machines. We can do what's called a net power calibration. So the machines will actually, when you're milling, consume power without any product. And if I want to look at the exact power consumption of my slurry, I would then do what's called a net power calibration, run the machine for a minute without any product, and then factor it to a 0 point. That's when I'm introducing my slurry, that I know all the power that I'm using is strictly related to my formula and not any energy input from the machine. That's important for upscale. We have great lab space at VMA in Germany, a lot of good equipment. So if you want to go over there and visit us and run trials, that's always an option. But we also have a great lab in Connecticut. This is an older picture. We have a lot more equipment. There's also a good video online on YouTube, our YouTube channel we have available with a lot of presentations and the walk through that lab, showing you all the great equipment that we have in there. We just added some different dissolvers. This is the AE6 that we have in there with all the modularity, and we have an SL, the latest SL mill as available as well. So the lab is designed to really be customer friendly, to have you come in to run your product, do a proof of concept with our equipment, show you how easy it is to work with the equipment, what results you would be getting. If you want to think about if you're using horizontal mills and you want to see how a basket mill would work for your process, maybe that's a good option. But the great story here is that since it's a big additives, we also have to tie in with our chemists from the additives business. And when you come in and you run product, we can utilize their resources or knowledge base and help you modify or improve a formula, or give us advice on how to create better results. So that's the great option of having a sister company on the additive side, that everything works really seamlessly. So we don't want to be just a hardware supplier. We want to be a full solution provider to our customers, not just somebody who sells you a piece of hardware and then walks away. We want to be there long term for you to help you make the best possible product out of your facilities. If you just want to come in and look at the equipment and not run any product, that's also a possibility. We also offer training seminars as well for that facility for you as our customers. We do not charge for a day. So if you come in and you want to really try out, the equipment, please don't think, we're going to charge you. We would not if it's a viable project. But if it's more than 1 or 2 days, depending on the viability of the project, then we have a charge to use the equipment and the lab space. So that concludes the milling portion today. I hope this was helpful and answered most of your questions, and I will open it up to the audience. Sorry, I went a little bit over.
No, you're good, Andy. Thank you for the comprehensive overview. This was a great second part of the dispersion series here. To everyone out there, I did put a link to the first part, dispersion deep dive. That'll go to our YouTube channel. You can check that out. I also did just put a link to a quick video of our Wallingford, Connecticut lab for you to take a look at. We do have just 2 questions, and I think we can get them in here under the hour. First one, in terms of choosing the right equipment, what could you tell us about nanoparticles dispersion at laboratory and manufacturing processes?
So thank you for this good question. So obviously, it's really important when we talk, depending on what nano range you're looking for. What is the application? So if you're looking at really something sub 500 nanometers and it needs to be scalable, unfortunately, with today's technology, you're going to be needing a horizontal mill. There's just no way around it. Anything less than 500 nanometers, the basket mill is no longer viable. So horizontal mill is our only option. Then it depends, obviously, we need to choose the right setup of our mill. Obviously, when you use nano, it's always ceramic components. We need to identify really the final particle size. Helps us also understand what is the product requirements in terms of the material that I need to use, because I have different ceramic components. For my nano kit or for my nano machine, I could use silicon carbide, which is black ceramic, or just regular zirconium oxide, which is the white ceramic. But I wouldn't be able to use the stainless steel option there at all. But again, application dependent, particle size dependent, and very importantly, viscosity dependent as well.
Excellent. And last question
Did
here.
this answer the question, or is there follow up to that?
Yeah. Let's see. Mauro, did that answer your question, sir? Let's see. Yes. Okay. Thank you.
Okay.
Good job, Andy. Next question here. What is the recommended temperature upper limit during the milling?
So this really, there is no rule of thumb. We have customers, that sometimes what we see, so basically ADC is most of the materials is ADC is the limit. Depends on obviously the formulation. You could damage, some ingredients that go in if you go higher. 100 C is a boiling point, so a lot of materials are not designed to go above it. So obviously, some people want to have a reaction, so that's different. But ADC, I would say, is probably the maximum for most application. Usually, when we are milling, we try to stay between 30 to maybe 60 C. And then again, there's a difference between solvent-based and water-borne products.
Okay. Excellent.
Did that answer the question?
Yeah, I think it did. Any follow-up questions? Nope. You're good. Good job, Andy. Well, I just want to thank you, Andy. Thank you for everyone attending. Hope you learned something here. If you think of something after the fact, any of those automated messages that you get, announcing, either with the recording of this webinar or future webinars, just hit reply. It'll come to the marketing team, and we'll get it to the right technical person, Andy or his team. So stay tuned for that link that will be coming momentarily. And we look forward to seeing you on future BYK Instruments web seminars. So thank you all. Thank you, Andy, and enjoy the rest of your day.
Thank you. Just quickly, there is the link of the YouTube channel on the bottom in the chat box.
Yes.
And that is also part of our YouTube channel. If you're interested in further seminar and you watch this seminar later on or look at other seminars that we have up there, that's a good resource. Join us there on the YouTube channel, sign up, and then you'll always get the latest information as well.
Good reminder, Andy. Thank you. And have a great day, everyone. Thank you.
Thanks again, and appreciate you all.